Okay, let's unpack this. We've got a fascinating stack of sources here, really diving into the world of artificial intelligence.
Yeah, there's a lot here.
We're going to explore, the core ways these AI models learn, the different types of models for specific jobs, and crucially, how these complex systems actually get built and scaled and, well, used in the real world.
Absolutely. And this deep dive, it's really focused on trying to cut through some of that complexity.
Right.
Our mission, really, is to pull out the most important nuggets of knowledge, the key insights from these sources, and hopefully give you a clearer picture of the whole AI landscape right now.
Exactly. Get ready for maybe a few aha moments along the way. Let's just jump right in with the basics, the foundations. How do these systems actually learn?
Okay, so at the most fundamental level, the sources lay out two main ways AI models learn from data. The first one is called supervised learning.
Supervise. Okay, so like having a teacher, someone guiding it.
That's a great way to think about it, yeah. You have labeled data. The input, say, a picture is paired with the correct output, like the label cat or an email marked spam.
Gotcha. So it learns the mapping from examples.
Precisely. It figures out the relationship between input and output from those examples, and then it can predict outputs for new stuff it hasn't seen before.
And that's perfect for tasks like, well, classification, right?
Yeah.
Figuring out categories, spam versus not spam.
Exactly. Classification is a big one. Or regression, which is about predicting a continuous value. Think trying to forecast a house price based on its size and location, that kind of thing.
Okay, makes sense. So what's the second way?
The second way is unsupervised learning. And just like it sounds,
No teacher this time.
no teacher, no labels. The algorithm just gets the data raw. Its job is to find hidden patterns or structures within that data all by itself.
Like finding groups, like
Yeah.
clustering, maybe grouping customers based on what they buy.
Yes, customer segmentation is a classic example of clustering. Or association, finding rules like, hey, people who bought this also bought that, market basket analysis.
Ah, the classic beer and diapers example.
Kind of, yeah. And also dimensionality reduction. Which sounds complicated, but it's really about simplifying complex data, boiling it down to the most important underlying factors. Autoencoders often get used here, the sources mention, for things like cleaning up noisy images. They learn the real signal.
That distinction, supervised versus unsupervised, is really clear. And the sources also mention a mix, right? Semi-supervised learning.
They do. It's sort of a middle ground. You use it when you have a ton of data, but maybe labeling all of it is just too expensive or time-consuming.
Like
medical scans, perhaps.
So you use the few labeled examples, you do have to kind of bootstrap the learning on the rest.
Exactly. The labeled data gives the model a starting point, helps it find initial patterns, and then it can apply that learning to the much larger pool of unlabeled data. It's very practical.
Okay, so we know what they learn from labels or no labels, but how does the learning actually happen inside something complex, like a neural network? Especially when it gets things wrong.
Right. That brings us to backpropagation. This is really fundamental. So picture a neural network. Layers of these nodes or neurons all connected, and those connections have weights, like little strength dials.
Okay.
When you feed data in at the front, that's forward propagation. It goes through the layers, gets transformed by the weights, biases, activation functions, and you get an output at the end.
But that output might be wrong.
It often is, especially early on. And backpropagation is the algorithm for fixing that mistake. It's the core error correction mechanism.
How does it work?
It calculates how far off the output was from the correct answer using something called a loss function. Then, and this is the clever bit, it sends that error signal backwards to the network. Yeah, figuring out how much each weight in the network contributed to the overall error.
And then it adjusts those weights accordingly to try and do better next time.
Precisely. It's an iterative process of refinement. Think about like learning to pronounce a tricky word. You try, someone corrects you. No, it's Martin, not Marvin, and you adjust how you say it. Backpropagation is doing that adjustment mathematically based on the error feedback.
Okay, that analogy helps. And the sources mention this applies to different kinds of networks.
Yep. Standard feed-forward ones, which they call static backpropagation, and also recurrent neural networks, RNNs, which have loops for handling sequential data like text. That's recurrent backpropagation.
And working hand in hand with backpropagation, there's usually an optimization algorithm trying to find the best weight adjustments. That's gradient descent.
Yes, gradient descent is typically how the network finds the optimal set of weights and biases, the ones that minimize that loss function, that error.
The sources use that analogy of being on a dark mountain trying to get to the bottom.
Right. It's a classic. You can't see the whole landscape, but you can feel the slope right where you are. So you take a small step in the steepest downhill direction.
And you keep taking steps.
You keep taking steps, guided by the gradient, trying to reach the lowest point, which represents the minimum error for the model. The size of those steps, by the way, is called the learning rate. That's a really important parameter to tune.
And there are different strategies for calculating that steepest direction, aren't there? Affecting speed and maybe accuracy?
Exactly. The sources break down three main types. First, batch gradient descent. This looks at all the training examples to calculate the error gradient before making a single update to the weights.
Sounds thorough, but maybe slow.
Very thorough and can be computationally efficient in some ways, but yes, very slow, especially on massive data sets. Then you have the opposite, stochastic gradient descent, or SGD.
Stochastic meaning random.
Well, it updates the weights after looking at just one training example at a time, so it's much faster per update, it bounces around more.
Yeah.
But the path down the mountain can be noisy and less stable.
Okay, so batch is slow but steady. Stochastic is fast but jumpy. Is there a middle ground?
There is, and it's often the most practical choice, mini-batch gradient descent. You split the data into small batches, say 32 or 64 examples, and you update the weights after each batch.
So a balance between the two? Faster than batch, more stable than stochastic.
Pretty much, yeah.
Yeah.
Here's a good trade-off. But, gradient descent isn't perfect. The sources mention challenges like getting stuck in okay but not great valleys, local minima, or on flat areas called saddle points. And in really deep networks, the gradients can sometimes shrink to almost nothing, which stops learning. That's the vanishing gradient problem.
Or they can explode.
Or explode, yeah.
Yeah.
Exploding gradients makes learning unstable. So there are techniques to deal with these, but they're inherent challenges.
Okay, that's a really solid grounding in how the learning works. Now let's shift gears and look at some specific types of AI models. What about models that are really good at recognizing patterns, especially in images?
Right. For images, the absolute star is the convolutional neural network, or CNN.
CNNs. Heard a lot about those. What makes them special for images?
Their architecture is just built for grids of data, like pixels in an image. They use these things called filters. Think of them as tiny pattern detectors, maybe looking for edges or corners.
And these filters slide across the image.
Exactly. They slide across, looking for their specific pattern. The first layers might find really simple stuff, like lines at certain angles. Then, deeper layers combine those simple patterns to recognize more complex features, shapes, textures.
And then even deeper layers recognize objects, like faces or cars.
Precisely. They build up this hierarchy of features, from simple to complex. That's why they're so powerful for visual tasks. Think optical character recognition, OCR, finding faces in photos, image search, analyzing medical images like X-rays or MRIs. CNNs are everywhere there.
Gotcha. The sources also brought up autoencoders again in the context of images. We mentioned them for dimensionality reduction earlier.
We did. And they are unsupervised networks. Remember, they have two parts. An encoder that compresses the input image down into a smaller, condensed representation, sometimes called a code or bottleneck.
And then a decoder that tries to rebuild the original image from that compressed code.
Exactly. The goal is just to reconstruct the input as accurately as possible.
But why is that useful? Just copying the input.
But by forcing the data through that bottleneck,
Yeah.
the network has to learn what's really important, what the essential features are. It learns to capture the core signal and ignore the noise.
I see. So it's great for denoising images, cleaning them up.
Excellent for denoising, also for feature extraction, pulling out those core features. And anomaly detection, if you feed it something really different from what it was trained on, it won't be able to reconstruct it well, flagging it as unusual.
Interesting. Okay, and then the third image-related model mentioned was generative adversarial networks, GANs. These sound competitive.
They really are. It's a fascinating unsupervised learning setup. You have two models locked in a contest. Yep. A generator model whose job is to create fake data samples, like realistic-looking images of faces that don't actually exist. And a discriminator model whose job is to tell the difference between the real images from the training set and the fake ones made by the generator.
So they're playing a game against each other.
Exactly. It's an adversarial game.
Yeah.
The generator tries to fool the discriminator, and the discriminator tries to catch the fakes. They both get better over time. The loser of each round updates their strategy.
Until the generator gets so good that the discriminator can't tell the difference anymore.
That's the goal. When the generated samples are indistinguishable from real ones, GANs, which often use CNNs inside them, are amazing for things like generating synthetic images, predicting what the next frame in a video might look like, or even enhancing low-resolution images.
Okay, shifting from images to, well, language, sequential data, natural language processing, NLP, that's huge right now.
Absolutely. NLP is all about enabling computers to understand, interpret, and generate human language, text, or speech.
Taking something unstructured, like me just talking now, and making sense of it.
Exactly. The sources talk about translating that unstructured input, like saying, add eggs and milk to my shopping list, into structured data the computer can actually use.
And there are two sides to this, understanding and generating.
Right. NLU, natural language understanding, is about going from unstructured human language to structured data. NLG, natural language generation, is the reverse, taking structured data and generating natural-sounding language from it.
And NLP isn't just one thing, it's like a toolbox.
It's definitely a collection of techniques. The sources highlight a few key ones. Tokenization is fundamental, just breaking text down into smaller pieces, like words or sometimes parts of words.
Makes sense. You need the basic units first.
Then you have things like stemming. This is a sort of crude way to get to the root of a word by chopping off prefixes or suffixes. So running, runs, ran might all become run.
Crude, you say.
Well, yeah, it can be a bit blunt. The sources give the example that better might get stemmed down to bet, which isn't really the root meaning, is it?
No, not really.
So a more sophisticated approach is lemmatization. This uses dictionary knowledge and analyzes the word's context to find its actual base or dictionary form, its lemma. So better would correctly lemmatize to good.
Ah, I see. Much smarter.
Definitely. And another important tool is part-of-speech tagging. This figures out the grammatical role of each word. Is it a noun, a verb, an adjective, based on how it's used in the sentence?
And all these tools power things like machine translation, which needs context, not just word-for-word lookup.
Precisely. Machine translation, chatbots, virtual assistants like Siri or Alexa, sentiment analysis, figuring out if a review is positive or negative, even spam filters in your email. They all rely heavily on these NLP techniques.
And for handling the sequential language data, a really important model architecture came up, the transformer.
Yes, transforms have been a huge breakthrough, especially for sequence-to-sequence tasks like translation or summarization. They also have an encoder and a decoder structure, like some other models.
But they have a special trick, right? The attention mechanism.
That's the key innovation. Attention allows the model, when processing a word, to look at all the other words in the input sequence and decide which ones are most relevant or important for understanding the current word's context.
Regardless of how far away they are in the sentence.
Exactly. Older models like RNNs processed words one by one sequentially, so information from distant words could get lost. Attention lets the model directly attend to relevant context anywhere in the input.
And this allows for more parallel processing during training, makes them faster.
Significantly faster to train on large data sets because you don't have that strict sequential dependency. Models like GPT-3, BERT, they're built on this transformer architecture. They're used for translation, summarization, text generation, question answering, even be adapted for image tasks now too.
Fascinating. Okay, one more category of models. Those designed for understanding relationships, connections, maybe for recommendations or working with structured knowledge.
Right. Knowledge graphs are really powerful here. Think of them as networks of information.
Like a mind map.
Sort of, but more structured. You have nodes, which represent entities, people, places, products, concepts, and you have edges, which represent the relationships between those entities.
And a single node, like London, could have edges connecting it to UK, located in River Thames feature, Mayor, governed by lots of connections.
Exactly. And the real power, as the sources point out, is that these graphs can combine data from different places and let you infer new facts just by following the connections. Maybe you combine census data and restaurant reviews to estimate something specific, like the number of vegan cafes near parks in a city.
And NLP helps build these graphs from text.
Often, yes. They're used in virtual assistants to answer factual questions. What's the capital of Canada?
Right.
Recommendation engines. You watch this video, maybe you'll like these. And even complex tasks like fraud detection and insurance. The sources give that simple example. Human consumed coffee. Human needs sleep. Coffee prevents sleep. You can see the relationships.
Got it. What about models for more standard classification or prediction, but maybe ones that are known for being robust? The sources mention random forest.
Random forest. This is a really popular and effective ensemble model.
Ensemble, meaning it combines multiple models.
Exactly. Instead of relying on a single decision tree, which can sometimes be unstable or prone to overfitting.
Overfitting, that's when the model memorizes the training data too well, right? And fails on new data.
Precisely. Random forest avoids that by building many decision trees, hundreds or even thousands. Each tree is trained on a random subset of the data and considers only a random subset of the input features at each split.
So you get lots of slightly different trees.
Yes, diverse trees. And then, to make a prediction, the random forest model aggregates the results from all the individual trees, like taking a vote for classification or averaging for regression.
And combining them makes the overall prediction better.
Much more robust and accurate, typically. It averages out the errors and biases of individual trees. Random forests are widely used in areas like finance, predicting loan defaults, medical diagnosis, economics, anywhere you need reliable predictions.
Okay. And one more for uncovering hidden structures, especially for recommendations. Restricted Boltzmann machines, or RBMs?
Right, RBMs. These are a type of probabilistic graphical model used for unsupervised learning. They're good at discovering underlying patterns or features in data.
How are they structured?
They have two layers, a visible layer, which represents the data you can see, maybe which movies a user has rated, and a hidden layer, which learns abstract representations or latent features that explain the visible data, things like movie genres, actors, or styles that aren't explicitly labeled, but explain why certain movies are rated similarly.
And the restricted part means nodes only connect between the layers, not within them.
Correct. Every visible node connects to every hidden node, but there are no connections within the visible layer itself or within the hidden layer. This restriction simplifies the learning process significantly.
And they were famously used in recommendation systems.
Yes, the Netflix prize competition really highlighted their effectiveness for collaborative filtering. They learned those hidden features representing user tastes and item characteristics, and then used them to predict what else a user might like based on users with similar hidden preferences. They were also used for feature extraction and pattern recognition more broadly.
Wow, okay. That's a great tour of the different model types. So we understand the learning basics and the kinds of models. How does this all come together in the modern world? How are these things actually built, scaled, and deployed today?
Yeah, this brings us to the modern AI workflow. And a really transformative element here is the rise of foundation models.
These are those huge pre-trained models we hear so much about, often built on transformers, trained on just massive data sets.
Exactly that. They're trained on incredibly broad data, making them capable of a wide range of tasks right out of the box. But the crucial part is that they can then be easily adapted or fine-tuned for more specific, specialized tasks.
So instead of starting from scratch every time,
You start with this incredibly capable base. It fundamentally changes the game. Development is much faster. The sources use an analogy. Imagine starting with a model that understands programming language syntax in general, and then fine-tuning it with specific examples to make it translate between, say, Python and Java, much quicker than building a translator from zero.
and we see so many different foundation models popping up. Why not just one giant one?
Well, often they're specialized or fine-tuned for different domains or data types. The IBM NASA geospatial model mentioned in the source is a fantastic example.
Right, the one trained on, was it 70 petabytes of data?
An unbelievable 70 petabytes of Earth science data, satellite imagery, climate data, weather patterns, just immense.
So its foundation is deeply rooted in understanding the Earth.
Precisely. And while it was initially fine-tuned for specific things like detecting floods or wildfires, that powerful base understanding means it can be adapted relatively easily for other tasks, tracking deforestation, predicting crop yields, monitoring greenhouse gases. That adaptability across different specific use cases is the power of the foundation model approach. That's why you see models specialized for different industries or data types.
That scale is just mind-boggling. Okay, so stepping back from that amazing example, what does the overall workflow look like, from getting the data to having a model ready for use?
The sources lay out a pretty clear 5-stage workflow. And stage 1 is prepare the data. This cannot be overstated.
Garbage in, garbage out, right?
Absolutely. It involves gathering huge, diverse data sets, carefully categorizing them, and critically filtering out unwanted content. Things like hate speech, bias, copyrighted material. Creating a clean, governed base data pile is step 1.
Essential for building responsible AI from the ground up.
Couldn't agree more. Stage 2. Train the model. Here, you choose your foundation model architecture, or maybe you're building one, and you train it on that prepared data. This involved tokenizing the data, breaking it into pieces the model understands, which can run into the trillions of tokens for large models.
Trillions.
Yeah, and this takes massive compute power. We're talking months of training time using thousands of GPUs. It's incredibly resource intensive.
The big bottleneck, financially and computationally.
Definitely. Stage 3, validate. Once the training is done, you have to rigorously test and benchmark the model's performance against specific metrics. You need to understand how well it does on different tasks, what its limitations are. This often involves creating a model card documentation detailing its capabilities and performance.
Transparency about what it can and can't do.
Crucial.
Yeah.
Stage 4, deploy or fine-tune. The validated model is then made available for use. This might mean deploying it as an API in the cloud, or perhaps putting it on edge devices. Or this is the stage where you'd take a base foundation model and fine-tune it with your specific data for your particular task.
And finally, stage 5, apply use.
This is where the application developers come in. They integrate the deployed or fine-tuned model into their software, building the actual AI-powered features that end users interact with. The sources mention platforms like IBM Watsonx, which is built on Red Hat OpenShift, providing tools across this whole life cycle, things like Watsonx.data for data prep, Watsonx.governance, and Watsonx.ai for the model building and deployment. It aims to streamline that entire workflow.
Okay, let's zoom in on large language models, LLMs, since they're so prominent now, often as foundation models. The sources really hammer home the importance of prompting. How you ask makes a huge difference.
It's absolutely critical. The simplest form is zero-shot prompting. You just give the LLM a single instruction and hope it figures it out based on its massive pre-training.
But that can be hit or miss.
It can be. The sources give that example.
What?
Ask about different types of banks, and you might get an answer about river banks if you don't provide enough context. The model's just guessing your intent.
Ambiguity is a killer.
Exactly. So few-shot prompting is often much better. Here, you include one or maybe a few examples in the prompt itself that show the model what kind of task you want done and what the output should look like.
Ah, so you guide it. If you give an example asking about a financial bank, it gets the hint.
Precisely.
Yeah.
It dramatically reduces ambiguity and helps ensure the response format is what you need.
And there's a specific technique mentioned for improving the reasoning ability of LLMs, chain of thought, or COTI prompting, often starting with, let's think step by step.
Yes. This is a clever technique. You essentially ask the LLM to show its work, to break down its reasoning process step by step before giving the final answer.
And this actually makes it better at reasoning.
It often does, especially on more complex problems that require multiple logical steps. The sources had that example of an older model trying to figure out how many golf balls someone could juggle it. Failed with a standard prompt, but got it right when prompted to think step by step using chain of thought.
Interesting. So it forces a more deliberate process.
Kind of. It makes the model's reasoning more transparent, which is great for explainable AI, XAI, and it seems to encourage exploring different intermediate steps, leading to more accurate results sometimes. Even if the newest models do some of this internally now, SOI is still a really valuable prompt engineering tool.
Okay, but what if the information I need the LLM to reason about isn't in its general training data? What if I want it to answer questions based on my company's internal documents, for instance?
That's exactly where retrieval augmented generation, or GANs, comes in. It's a very popular and powerful pattern for building LLM applications that can effectively chat with your own private data.
Without having to do that massive, expensive retraining or fine-tuning of the whole LLM.
Exactly. That's the beauty of it.
So how does RAG work?
Well, first you take your documents, PDFs, text files, whatever, and you break them down into smaller, manageable chunks. Then you convert these chunks into numerical representations called embeddings. Think of embeddings as like coordinates on a map where similar concepts are close together.
Okay, so you turn your text into numbers that capture meaning.
Right. And you store these embeddings, along with the original text chunks, in a specialized database called a vector database. ChromaDB was mentioned as an example.
Vector database, got it.
Then, when a user asks a question, the RAG system first uses the question's embedding to search that vector database and find the chunks of your documents that are semantically most relevant to the question.
So it retrieves relevant snippets from my data.
Precisely. And then this is the augmented generation part. It takes those retrieved chunks and feeds them to the LLM along with the original question, essentially saying, based on this specific context I just gave you, answer this question.
Ah, So the LLM generates the answer grounded in the retrieved information, not just its general knowledge.
Exactly. You're augmenting the LLM's ability to generate language with targeted, relevant knowledge retrieved from your specific data source. It's much more efficient and cost-effective than fine-tuning for adding factual knowledge, especially if that knowledge changes often.
That makes a lot of sense for enterprise use cases. Now, scaling all this AI stuff, deploying models not just in one place, but maybe across the public cloud, private data centers, even out to edge devices. That sounds complex. The sources talked about distributed AI.
It is complex. The goal of distributed AI is to manage AI applications and their associated data seamlessly across all these different environments. It's often described using a hub-and-spoke model.
Hub and spoke.
Yeah. The spokes are the locations where the data lives or where the AI needs to run. Could be a factory floor, a retail store, a regional data center. The hub provides the central AI capabilities, the model management, the governance, the control plane.
What makes scaling AI in this distributed way so challenging?
Several key things come up in the sources. Data gravity is a big one. Moving massive data sets, especially if they're sensitive, between the spokes and the hub can be slow, expensive, and sometimes not even allowed due to regulations.
Right, the data wants to stay where it is.
Exactly. Then there's heterogeneity. Each spoke might have different hardware, different network conditions, maybe slightly different data formats. You can't just deploy the exact same massive model everywhere. You often need adaptation.
And just the sheer scale, managing potentially thousands of spokes.
Yes, the number of locations, the variety of data, the different applications, it gets complex fast. And finally, resource constraints, especially at the edge. A sensor on a factory machine doesn't have the compute power or memory of a cloud server.
So how do you tackle these challenges?
The sources point to a few strategies. Intelligent data collection at the spokes, maybe doing some initial processing locally and only sending back the important results or summaries, not raw data. Building adaptation and monitoring capabilities right into the spokes so models can adjust to local conditions.
Automating things sounds crucial too.
Absolutely. Automating the data and AI lifecycle, using policy-based management for deploying models, monitoring their performance, triggering retraining automatically when needed, and optimizing the AI pipelines themselves, things like feature extraction, model compression, or quantization to make them smaller and faster so they can run effectively within those resource constraints at the edge.
Related to keeping data distributed, especially sensitive data, federated learning came up as a key technique.
Yes, federated learning directly addresses the data privacy challenge in distributed settings. It completely flips the traditional approach.
How so?
Instead of bringing all the data from the spokes to a central hub for training, federated learning sends the model out to the data.
Takes the model to the data.
Right. Each device or location, like a phone, a hospital, a bank branch, trains a local version of the model using its own private data, which never leaves the device.
Okay, so the data stays put. What gets sent back?
Only the updates to the model, the learned parameters or gradients, get sent back to the central server, not the raw data itself. The server then aggregates these updates from many devices to improve a shared global model.
And this was driven heavily by privacy concerns?
Hugely. The sources note Google pioneered it around 2016, largely for privacy on mobile devices. It allows multiple organizations or multiple devices to collaboratively train a better model without ever exposing their sensitive underlying data to each other or to a central party. Think about hospitals training a diagnostic model on patient data, or banks training a fraud detection model on transaction data without sharing the actual records.
That's powerful. Are there different types?
Yeah, the sources mention variations like horizontal federated learning, where devices have similar types of data but different specific examples, and vertical federated learning, where devices have different types of data about the same examples. There's even federated transfer learning, adapting existing models.
What are the downsides or challenges?
Well, communication efficiency can be a bottleneck. Sending model updates can still be bandwidth intensive. Ensuring the aggregated model performs well for everyone is tricky. And there are security concerns like inference attacks, where someone might try to deduce information about the private data just from the model updates. The techniques like encryption and adding statistical noise help mitigate that. Transparency can also be a challenge.
Okay. Now, to actually do all this complex training and scaling, especially for the huge neural networks we've discussed, developers need tools. PyTorch was mentioned as a major framework.
PyTorch is definitely one of the leading open source frameworks for machine learning and especially deep learning. It provides the fundamental building blocks, tensors, automatic differentiation, and a whole ecosystem of tools for building and training neural networks.
And it's particularly relevant when we talk about the sheer scale, right? Those models with billions of parameters.
Absolutely.
Hmm.
As models get bigger, the sources use the llama model, scaling from 7 billion to 70 billion parameters. As an example, the compute and memory needed just explodes. Training that 70 billion parameter model takes an astronomical amount of GPU time and resources.
So how does PyTorch help manage that scale during training?
It has built-in utilities for distributed training. One core technique is distributed data parallel, or DDP.
DDP. Yeah.
With DDP, you basically make a copy of your entire model on several different GPUs. Then you split your big training data set across those GPUs. Each GPU processes its chunk of data using its copy of the model, calculates the necessary updates, gradients, and then those updates are efficiently synchronized across all the GPUs to keep the models consistent.
So it parallelizes the data processing, works if the whole model fits on one GPU.
Exactly. It's great when the model fits in a single GPU's memory, and it cleverly overlaps the gradient synchronization communication with the next round of computation to keep things running fast.
But what if the model itself is too massive for even one GPU? That 70 billion parameter model probably doesn't fit.
Right. For those huge models, PyTorch offers fully sharded data parallel, or FSDP.
Fully sharded, meaning the model itself gets broken up.
Precisely. FSDP shards, or splits, the model's parameters, the weights, gradients, and optimizer states across all the available GPUs. So no single GPU needs to hold the entire model. During computation, each GPU only pulls in the specific parts of the model it needs at that moment, using efficient communication primitives like all-gather.
That sounds complex, but allows for much bigger models.
It does. It requires more sophisticated communication coordination, but it unlocks the ability to train models far larger than single GPU memory. And it also provides more opportunities to overlap communication and computation for efficiency. IBM, by the way, has been a major contributor to FSDP and PyTorch.
The sources also mentioned improvements beyond just distributing the work, specifically around compiler technology in PyTorch 2.0, Torch Dynamo.
Yes, Torch Dynamo is a key part of PyTorch 2.0, accessed via a really simple API call, torch.compile. What it does essentially is take your standard Python-based PyTorch code and, behind the scenes, compile it down into much more optimized low-level instructions for the GPU.
So it makes the code run faster.
Significantly faster, often. The insight is that standard Python execution involves a lot of overhead. The compiler analyzes the code, fuses operations together, and generates more efficient execution graphs, meaning the GPU spends less time idle waiting for instructions and more time actually doing math.
And the speedups can be pretty dramatic.
The sources mentioned seeing up to 40x speedups in some cases, which is huge for both training time and inference time when you're actually using the model to make predictions.
Yep.
IBM has also contributed significantly here to the compile itself and benchmarking its effectiveness, especially on different network types like Ethernet versus InfiniBand.
Okay, so PyTorch provides the engine. How do we get these AI capabilities into the hands of users, into everyday applications? The idea of embeddable AI came up.
Right. Embeddable AI is really about that AI plus mindset. It's not necessarily about building standalone AI products, but about infusing AI capabilities into existing applications and workflows to make them smarter, more efficient, more intuitive, more automated.
Making the software we already use better with AI.
Exactly. And the sources describe two main ways this embedding typically happens.
Okay.
One way is through containerized libraries. These are essentially pre-trained AI models, often built using open-source frameworks like PyTorch or TensorFlow, packaged up neatly in software containers.
Like Docker containers.
Precisely. The big advantage here is flexibility. Because they're containerized, they can run pretty much anywhere on your own servers, on-premise, in the public cloud, out at the edge, in hybrid setups. They tend to be lightweight and can help reduce infrastructure costs because you're just running the specific model you need.
Okay, containerized libraries. What's the other way?
The other way is through applications. These are more like full-fledged software products built with AI capabilities, often designed for specific business users or even developers. A key feature here is that they often provide low-code or even no-code interfaces.
Meaning you don't need to be an AI expert to use them or integrate them.
Right. They abstract away a lot of the underlying complexity. This can dramatically speed up time to market for adding AI features and lower development costs if you don't have a team of specialized AI engineers readily available.
So the choice between a library and an application depends on your needs, like how much control you want, where you need to deploy it, your team's skills, how fast you need it.
Exactly. The sources used a call center example. If you need NLP for sentiment analysis and you need flexibility for a hybrid cloud setup or a small footprint, a containerized library might be best. But if your priority is getting that capability integrated super quickly and your developers aren't AI specialists, a pre-built application might be the faster path.
Makes sense. And regardless of the method, the need for responsible, trustworthy, and secure AI was emphasized. Governance, fairness, explainability, robustness, privacy, security, all crucial when embedding AI.
Non-negotiable, really. You have to build that trust.
Okay, pulling a lot of these threads together now. The sources introduced a concept that feels like a significant step up in capability. AI agents.
Yes, AI agents represent a shift. They're described as compound AI systems.
Compound, meaning multiple parts working together.
Yes, but the key difference from traditional complex software is what's in charge. In an AI agent, a large language model is used for the control logic.
So the LLM isn't just one tool in the system, it's the orchestrator, the planner.
Exactly. Instead of having fixed programmatic logic dictating step A, then step B, then step C, the LLM itself figures out the plan based on the goal. This is becoming possible because of the much improved reasoning abilities we're seeing in the latest LLMs.
So they think slow, as the sources put it. They plan, they use tools, they iterate.
That's a good way to put it. The core components of an agent are typically described as reasoning, the LLM making the plan; acting, the ability to use external tools or APIs like performing a web search, using a calculator, querying a database; and accessing memory, storing and retrieving information from past interactions or logs to inform future steps.
And there's a loop involved.
Yeah, the basic agent loop looks something like this. User gives a query or goal. LLM is prompted to make a plan and decide on the next action, which might involve using a tool. Agent calls the chosen tool. Agent observes the result from the tool. LLM takes that result, reflects on it, maybe updates the plan, decides the next action, could be another tool, could be giving the final answer, and it continues until the goal is met.
The sources had that sunscreen example, figuring out how many bottles to pack for a vacation. That's not a simple lookup.
No, it requires multiple steps. You need to know the trip duration, the destination, check the weather forecast there. Tool.weather API. Understand sunscreen SPF ratings, maybe consider skin type. Calculate recommended application amounts. Tool.calculator. Perhaps even check prices. Tool.shopping API. An agent could potentially handle that whole complex multi-step reasoning and tool-using process.
So agents are good for these more complex, less predictable tasks where you might need different tools depending on the situation.
Exactly. The core idea is moving AI beyond just executing single, well-defined functions towards systems that can autonomously plan and execute sequences of actions using various tools to achieve more complex goals. It's seen as being on a spectrum of AI autonomy. For very narrow, predictable problems, hard-coded logic might still be more efficient. But for broader, more dynamic challenges, the agentic approach is powerful.
And bringing it all back to a concrete application, the sources used auto claims processing as a real-world example.
Yeah, it's a good illustration of how these AI capabilities can be woven together on a hybrid cloud platform to fundamentally improve a process. After a car accident, which is stressful,
Very stressful.
an AI-powered system could guide the customer through documenting damage using their smartphone camera, automatically analyze the images, help select approved repair shops nearby, maybe even assist with arranging a rental car or tow truck.
Leveraging computer vision, NLP, maybe knowledge graphs of repair shops, decision logic, all orchestrated.
Exactly. It uses data and AI across the workflow to make the process faster, smoother, and less stressful for the customer, while also improving efficiency for the insurance company. It's a practical example of many of these pieces embedded AI, potentially using agent-like reasoning put into practice.
So reflecting on everything, what does this all mean? We've covered a huge amount of ground in this deep dive.
We really have. We started right down at the foundation supervised, unsupervised learning, how backpropagation and gradient descent actually make neural networks learn. That's the bedrock.
Then we explored the zoo of different models. CNNs mastering vision, transformers revolutionizing language, knowledge graphs mapping relationships, random forests providing robust predictions, RBMs finding hidden factors, each suited for different tasks.
And we saw how the modern AI workflow really leverages massive foundation models trained on incredible scale, then fine-tuned. We walked through that whole 5-stage process from data prep using platforms like Watsonx right through to validation and deployment.
Plus, the critical skill of prompting LLM's zero-shot, few-shot chain of thought for better reasoning, and the power of RG for letting them converse with your specific data.
And crucially, how we scale this. tackling the challenges of distributed AI across clouds and edge devices, using federated learning to train models while protecting data privacy, all enabled by powerful frameworks like PyTorch with its distributed training and compiler optimizations.
And finally, seeing how AI gets embedded into the applications we use and looking ahead to these emerging AI agents where the LLM itself takes charge of planning and acting using tools, it really feels like the landscape is shifting from individual tools towards more integrated, capable, and, well, autonomous systems.
It does, and as these AI systems, especially agents, become more capable of reasoning, planning, and acting on their own initiative to solve complex multi-step problems, what questions does that start to raise for you about that future, about the balance between efficiency and human oversight, or how we'll work alongside systems that can genuinely plan and act in the world?